Welcome to AI Explains. Today we are taking a deep dive into some really fascinating science about CO2 in seawater. And honestly, to keep things simple for you today, we are going to explain this like you are 12 years old. The best place to start is this cartoon from the preface of our sources. It is literally just a dog and a tail.
Yeah, um, it is the perfect analogy, really, because the authors use it to frame the entire global carbon cycle. The ocean is the dog, and the atmosphere is the tail.
Right, because the ocean is just so massive. I mean, it holds like 98% of the carbon in this whole system. The atmosphere is just this wispy little...
This tiny appendage, yeah. Historically, the dog controls the tail. The ocean tells the atmosphere how much carbon it gets.
Yeah.
But the whole point of this deep dive is that human activity has totally flipped that script. We are pumping so much gas into the air that the tail is now furiously wagging the dog.
And so our mission today for you listening is to figure out how an invisible gas changes the chemistry of a massive ocean. And we should probably bust a huge myth right off the bat. When CO2 hits the ocean, it is not like shaking up a bottle of soda, right?
No, not at all. You open a soda and the gas just bubbles out
Uh-oh.
because it is not chemically bound. But seawater is this complex chemical soup. When CO2 hits it, it reacts. It shapeshifts.
It turns into entirely new things.
Exactly. Mostly these things called bicarbonate and carbonate ions.
So it transforms rather than just sitting there. And our source uses this awesome rush hour analogy to explain how these new particles act, like the difference between concentration and activity.
Yes. So imagine an ion, which is basically a charged particle, is a sports car. If you drive that car in fresh water, it is like cruising through Death Valley.
Wide open roads, no traffic. You can go 100 miles an hour with total freedom to move around.
Precisely. But the ocean is salty. It is packed with other ions like sodium and chloride. So that same sports car is now stuck in New York City rush hour.
Bumper to bumper.
You cannot move freely. You're constantly interacting with the cars around you.
And the text gets even more specific with something called ion pairing. So in this massive traffic jam, your sports car might get stuck hauling a trailer.
Essentially, yes. In the chemical crush of seawater, a carbonate ion might get hitched to a magnesium ion. So instead of zipping around, it is hauling this huge U-Haul trailer. It is still physically there, but it is not active. It cannot do its job because the traffic is weighing it down.
Which shows how stubborn the ocean is. It resists change. And that brings us to the revel factor, which is basically the ocean saying, I am full.
That is the measure of the resistance. And here's a crazy statistic for you. If you double the amount of CO2 in the air, the carbon actually dissolving into the ocean does not double.
It only goes up by like 10%, which feels counterintuitive. If the tail is wagging the dog, why does the dog not react more?
It goes back to the traffic jam. To absorb CO2 and keep things stable, the ocean pairs it with carbonate. Think of carbonate ions as empty taxis.
Okay, so we are pumping in tons of passengers, the CO2, but we have used up all the empty taxis.
Exactly right. We are running out of free taxis. That limitation is the Revel factor. The ocean's ability to buffer, to soak up that carbon without changing its pH, is limited by the empty seats. Once they're gone, the system breaks down.
And when it breaks down the ocean, chemistry shifts. You can actually see this physical limit at the bottom of the ocean. Our source calls it the saturation horizon, but it visually looks like an underwater mountain range covered in snow.
It really does look like a winter wonderland. The peaks are white because they are covered in crushed-up shells from plankton and corals, which are made of calcium carbonate.
But then you look down into the deep valleys and the snow is just gone. It is all dark clay.
Because the snow melted. There is a literal invisible line in the water. Above it, the shells survive. Below it, the pressure creates a highly corrosive environment.
Just the weight of a deep ocean forcing the chemistry to flip.
Yeah, the immense pressure actually forces the water to eat the shells. It dissolves them right back into the ocean. That is the snow line.
So here's the scary part, where we connect the tail to the dog. As we add more CO2 and run out of those taxi seats, the water becomes more acidic.
And acid dissolves calcium carbonate.
Meaning we are literally raising the snow line.
We are pushing that corrosive zone higher. So the creatures living near the surface, the corals and plankton that form the base of the whole food web, are suddenly in water that wants to dissolve their skeletons.
It is like the floor is rising to swallow them. We usually think of the ocean as this endless sponge that cleans up our messes, but the chemistry tells a different story. The sponge can get full.
And when the sponge is full and the buffer is gone, the changes happen much, much faster.
Definitely something for you to think about next time you look at the ocean. The tail can only wag the dog for so long before the dog bites back. Thanks for joining us on this deep dive.
Talk soon.